Hi, my name is Alexander Spiegelman. I'm a research scientist in Aptos Labs. And today I'm going to present Shoal, our research consensus BFT, DAG-BFT consensus development. So this is a joint work with Balaji, Rati, and Zekun from Aptos Labs. And let me start with some background on DAG-BFT consensus. So Narvel had two main contributions. The first is the coupling data dissemination from metadata ordering is the key for performance. So this is like one thing we did in Narvel. And the second contribution is a building very efficient DAG, directed asynchronous graph, of nodes in which each node basically has a bunch of transactions. And just the general structure is that it's a round-based DAG. Each validator is able to propose one node in a round, and each node points to n-f nodes in the previous round. So, and I don't want to go too much into the details. Maybe I just mentioned that because validators have to reliably broadcast these nodes, one property of the DAG is that even though the DAG is built asynchronously, you don't need to wait for more than n-f in order to make progress. And some validators might see different views locally on the DAG in any given time. Byzantine validators cannot equivocate, meaning that they cannot lie about the content of the nodes or the links of the nodes. So eventually, all validators will see the same DAGs. Okay, so this was Narvel. And on top of Narvel, there are a few protocols, DAG Rider, Tax, Bullshark. The goal of all these protocols is to look at the DAG. Like, again, each validator has a slightly different local view of the DAG, but still with no extra communication, basically, each validator can look on the DAG and totally order all the nodes and basically achieve consensus on the order of all the nodes, all the transactions, without any extra communication besides asynchronously building the DAG. So there are these three protocols: DAG, Rider, Task, and Bullshark. And today I'm going to present Shoal. So just to give you some motivation, here is a graph from the Narvel paper that compares throughput and latency. So in orange, you can see a vanilla Bullshark implementation. And you can see that the TPS is around 1,000 transactions per second, whereas Task on top of Narvel can achieve like at something like 160,000 transactions per second. So it is like 160x more TPS than hot stuff. However, you can also see that the latency of hot stuff is much better than the latency of Task. So the motivation for the Bullshark work was already to improve the latency. So Task is an asynchronous protocol that tolerates a strong adversary that has a lot of control over the network. But in practice, usually it's good enough to assume a partial synchronous communication, which in fact, I think the vast majority, if not all, of deploy consensus assume partial synchrony. So I'm going to talk a little bit here about Bullshark. The specific details of the protocol are not very important. There is only one specific thing that I need us to remember and understand from the Bullshark work in order to understand Shoal. But because I think Bullshark is a very simple protocol, I still can try to get and explain the main idea on one simple slide for anyone who never heard of Bullshark before. So again, there is the DAG. It's a structured DAG, round-based DAG, and the goal is to order basically to look at the local copy of the DAG, each validator, and order the nodes with no extra messages or anything, just by looking at the DAG. And the general idea is basically to interpret the links and the nodes of the DAG. Nodes, you can think of nodes as proposals, you can think of links as votes, and each validator can mentally, in his own mind, run something like a consensus protocol with this propose and votes. So the way it works with Bullshark is that there is a predefined mapping between encores and rounds. So we know that in round 1, The node proposed by validator 2 in this example is going to be the N call. In round 3 is going to be the node proposed by validator 4, and in round 5 is going to be the node proposed by validator 3. This mapping is predefined, and everybody a priori agree, and it can be anything. It can be a round robin for simplicity, right? So we have this mapping. And then when a validator locally looks at this local copy of the DAG, he needs to do two steps to order all the nodes. First, he needs to order the encores. Okay, and once he orders the encores, after he can go and order the causal history of the encores deterministically. Remember, the DAG constructions guarantee that there are no equivocation. So if we see the same causal history, two validators see the same causal history, it has to be exactly the same causal history. So this is like a property of the DAG. And just quickly really go over this slide. This is roughly what's going to happen. In order to commit an encore, we need F+1 votes. In this example, we have 4 validators, so F is 1, so we need 2 votes to commit. So here is validator, let's say validator 1, this is his local copy of the DAG, and he asks himself, can I commit A1, encore 1? And the answer is no, because we only have 1 vote, 1 link from nodes in round 2 to A1, so A1 cannot be committed. A2 cannot be committed as well. There is actually 0 votes. A2 is not even in the DAG. However, A3 can be committed. You see, we have 3 votes can be committed. Nice. So again, because different validators see slightly different DAGs, it's possible that some other validators sees 2 votes on A1. For example, there is this missing node that validator 1 doesn't have in round 2 from validator 4. Maybe some other validator has this node, and this node actually linked to A1 and votes for it. So in order to guarantee safety, what we do is that we check whether there is a path between A3 to previous encores. So in this example, there is no path from A3 to A2, meaning that A2 can be skipped. We don't need to order it. However, there is a path from A1 to A3 or from A3 to A1, doesn't matter what direction. And then it means that A1 has to be ordered before A3 to guarantee safety. And again, I don't want to go into this talk. There are other talks on Bullshark if you're interested, and you can watch them and understand how specifically the Bullshark protocol works. For the purpose of this talk, I need to emphasize one thing. So validator order the encores, and the Bullshark protocol guarantee that they all order the same encore. All of them, by interpreting their DAG, will agree to order A1, skip A2, order A3. And in particular, they will all agree that A1 is the first encore that needs to be ordered. Okay, that's important. That's basically the only important thing we need to remember from Bullshark. In order to understand Shoal. And now what Bullshark will do in this case, after order A1 and A3, it will go and order the causal history of these encores. So in this example, round 1 is the first round, so A1 doesn't have causal history, but A3 has a causal history, and we can apply some deterministic rule. It doesn't matter, any deterministic rule will do, and we can order all the encores. Okay, so. Okay, so back to motivation. You can see that Bullshark already improves the latency on top of task quite a lot, by 50%. But still, if you compare it to hot stuff, there is still a latency gap. And the thing is that hot stuff is is far from being the fastest blockchain, actually, faster consensus actually, because hot stuff insists of this linear communication. And if you are willing to pay the quadratic communication, which, by the way, in practice, we know today that it's not a big deal at all, and you can get much better latency. So, for example, the consensus that we currently is using in Aptos is Jolten, which already has a 50% better latencies than hot stuff. So when we started this project and started working on that consensus, we understood that the latency of Bullshark is not good enough for us, because our Jolten consensus is much better latency, and we cannot compromise on that. So we had to come up with ways to reduce the Bullshark latency, and this is basically what this talk is about. It's about Shoal. Or in other words, a framework to reduce DAG-BFT latency, which we can apply to Bullshark, but we can also apply to DAG Rider and Task. Basically, every novel-based consensus can leverage the Shoal framework, and basically the Shoal framework, as I will explain in the next slides, will add a pipeline mechanism, leader reputation, and will eliminate timeouts from almost completely in all practical scenarios. It will eliminate timeouts. Okay, so we're done with the motivation. Now we can go deeper into what Shoal is and how it improved the latency. But before that, we need to understand where is the latency coming from in Bullshark. And one place is basically the encores. So in the common case, Bullshark, if you remember the slides that I showed you like a few slides ago, it has an encore every second round. So there is a round in which there is an encore, and then next round is going to be the voting round, and then the next encore can also appear in the next round. And if you try to put an encore in every round by playing with the Bullshark logic, that seems to be impossible because again, I didn't go into the details, but there was some quorum intersection logic that needs to be preserved there, and it seems to be impossible to do it that way. And what we get as a result is that if you think about the latency, so for an encore node, it requires 2 rounds to commit and order it, like the round in which it was proposed and the next round in which nodes are going to vote for it. However, for a node in a vote round, it will require additional DAG round in the common case, because a node in the votes round is ordered together with an encore that points to it. Okay, so votes rounds, nodes in votes round will require 3 rounds on the DAG. And if you look at the nodes that are in the encore round, but they are not the encore, right? Like they will require 4 rounds on the DAG to be committed, because they are not linked from the current encore. They will need to wait for the next encore to be ordered in order to be ordered as well as its causal history. Okay, so one thing that we are doing, that we are introducing pipelining, meaning that we will have Shoal has encore in every round, and then as a result, all other nodes will require 3 rounds on the DAG to be ordered. None of the nodes will require 4 rounds. So that's already a latency improvement. And okay, so this was for the common case. Now for the worst case, let's talk about worst case. So what happened, and go back to the slides, what happened if you have a slow validator or a crashed validator? In this case, A1 is slow, it doesn't get enough support, it only gets 1 vote, so it cannot be ordered on Bullshark. And A2, maybe validator 4 even crashed, so A2 is not even in the DAG, so obviously is not ordered. So in order to order nodes in round 1, or even in round 0, which we don't see on the slide, they will need to wait until the encore in round 5, A3, to be ordered in order to be ordered as its causal history. That's a big latency penalty. So in order to deal with it, we introduce leader reputation into the DAG. Basically, the idea is simple: is that we are gonna use historical information about the performance of validators in order to decide whether they can be performed as encores or can they in the future rounds. So in this example, we could, for example, agree that because validator 2 and validator 4 are slow, we can agree that we can exclude them from being future validators, and their nodes cannot be encores anymore. Okay, so leader reputation, in fact, by a concept, is not something that we invented here. In fact, it's already used in Aptos today with Jolten. The key difference there is that if we are wrong today in the Jolten implementation about our leader reputation, no harm to safety will nothing. It's safe. It's totally safe. It's just we can lose liveness for some time until we agree on the leaders. Here, because we we have to a priori agree on the encores, and if we disagree on the encores, we will end up with a completely different total ordering. It's a more complex problem because we have to be precise with our reader reputation on the DAG. Okay. So let's now I'm gonna go and explain the solution, and for that I again want to remind the key property from Bullshark that we need to remember to understand the solution is that again we have the encores, predefined mapping of encores, and each validator interprets as the DAG, and as a first step decide which encores to order, which encores to skip. And the key property is that all validators agree on what is the first encore we need to order. In this example, even though you see we had to run until round 6 in order to order the encore in round 1, right? And in the process, we actually ordered around encore A3. Still, right, we all agree, all validators agree that A1 is the first one to be ordered. And this is like the property that we need to remember. And the key observation is that, again, we can go back and reinterpret the DAG deterministically. So as I said, here we had to go into the future, order A3 in order to realize that we first need to order A1. But it doesn't matter that we need to respect the A3 order. Everything is local computation. Everything is cheap. So we can go back and reinterpret the DAGs again, starting from round 2, and maybe come up with a completely different decision. And it's all good, and, as long as we do it deterministically and as long as all validators reach the same conclusion. So this is kind of the key observation. And let's see how it works. So pipelining. So what we are gonna do is that we start from scratch, okay? And we have some predefined mapping between leaders and rounds, denoted with these like gold crowns here. And then we will start by running an instance of Bullshark, and we have the encores. Again, we have an encore in round 1, then round 2 is gonna be a voting round. We have an encore in round 3, and so on and so forth. So we're gonna run a Bullshark. We're going to run a Bullshark instance starting from round 1. And, you know, as I said, by the property, it doesn't matter how many rounds in the future we need to go. Eventually, we will agree on the first encore to order. In this example, this is the encore in round 1. Doesn't have to be, but in this example is the encore in round R. Now, what we are going to do next, and this is the trick, is that we are going to forget about this instance of Bullshark. No, before we forget about this instance of Bullshark, we are going to order this encore together with all its causal history, because this is already agreed. This is a consensus. It's already agreed. But now, because all validators agree at this point, we can deterministically say, okay, forget about this instance of Bullshark, forget about everything that happened in future round in order to order this first encore. We are going to start a new instance of Bullshark in round 2. And to do that, we are going to change the encores mapping. And now you see now we have an encore in round 2 and an encore in round 4. And we're going to run a new instance of Bullshark starting of round 2. Again, we are going to run it until we decide which encore we need to order first. We order its causal history, and we repeat the same trick again. We are going to start a new instance of Bullshark starting from round 3. And we keep moving the encore. You see, this is how we get that we have an encore in every round, because we keep moving them. And in the good case, well, we are going to order basically all encores. And okay, this is very cool, and this is why we basically call this protocol Shoal, because what we get here is a shoal of Bullsharks. And apparently, I didn't know, obviously, but if you check the dictionary, shoal is a group of fish or sharks swimming together. So it's like a perfect name for this mechanism. Okay, so let's talk about leader reputation. So in leader reputation, like I said before, we're going to use the history in order to change the future mapping of encores. So again, we are going to use, the beauty is that we are going to use exactly the same trick as that we did for pipelining. So we're going to start the instance, and again, running Bullshark in round 1. We're going to run it until we order the first encore. Then we're going to look at this like first encore causal history, and the information in this causal history should give us should tell us who is performing, who is underperforming, who is probably crashed because we didn't see a node from these validators like in the last 20 rounds. So we get a lot of information there, and based on this information, and we can use different heuristics. The simplest heuristic is that, okay, let's just see who contributed a node in the last 10 rounds, for example, right? And if a validator didn't contribute a node, we can assume it was crashed, and this validator is not going to be, the nodes of this validator are not going to be encoded in the near future. So what we are going to do after we order an encode, we check the causal history, and we are going to decide on a new mapping. We are gonna basically, maybe we will determine everything is deterministically by some logic, but we can maybe decide that validator 4 is underperforming, so his nodes are not gonna be encodes. So we change the mapping, and then again, same trick. We can forget about this the previous instance of Bullshark, and we can start a new instance of Bullshark starting from round 2. And the cool thing is that we can combine this together with pipelining. So not only after we finish an instance of Bullshark, we do the following. If we want to combine them together, and obviously we want to combine them together, is that we run Bullshark, we order an encore, we use its causal history to come up with a new mapping from leaders from validators to leaders based on their previous performance, and then we're also going to shift all the encores to start from the next round, and then we are going to run the next instance of Bullshark starting with round 2 with new mapping with new encores basically based on their performance in the previous rounds. Okay, so far this is the algorithmic contribution of Shoal. It's already gives us a very good latency improvement. And the cool thing is that if you already have a Bullshark implementation, you can implement these changes very, very easily. Like I guess less than 100, 200 lines of code, you can already get this benefit. And I find it kind of, I mean, on the one hand, I find it kind of cool. On the other hand, it's kind of frustrating because when we were working on Bullshark, we didn't see it. But once you see it, it's very simple. So yep, I find it kind of cool. Okay, now let's talk about the system improvement, and this is like, which is in Shoal we get rid of timeouts from every practical scenario basically. So as most of us know, timeouts are very painful. And if you are, and they are unfortunately inherent in leader-based consensus. So if you have a leader-based consensus, hot stuff, PBFT, jolting, you cannot avoid timeout inherently, and this is the reason why. So in all these protocols, you have a leader, and you are waiting for the leader to send you some messages. And while you are waiting, you cannot distinguish. If you don't get a message from a leader, you ask yourself, like, if the leader crashed, right? It's one possibility. The other possibility is just it didn't crash, it's just very slow, or the network is slow. Maybe there are disconnections in the network, right? And it's impossible to distinguish. This is why like asynchronous protocol are always hard. There is this like impossibility to distinguish between a crashed node or just a slow node, slow network. So you must use timeouts in this case, because you just otherwise, if you don't use timeouts, then either you just wait forever for a crashed leader, or you just keep, I don't know, arbitrary skipping. I mean, otherwise there is nothing else to trigger you to move forward. Either if you're waiting for a message from the leader to move forward and never get it, and the leader is crashed, you will wait forever. So in leader-based consensus, you must use timeouts. And the problem with timeouts is that if you configure them to be too short, this is bad because the leader might be good, just a bit slow, but you keep skipping it because your timeouts are too slow. They're basically, the timeouts are too short. They're actually shorter than the network latency. On the other side, if your timeouts are too long, it's also bad because if the leader is actually crashed, then you have to wait this long timeout before you can move forward, and this is a huge penalty, latency penalty. And the typical numbers and systems today is like between 1 second, 1.5 seconds. So imagine every time a leader crashes, you cannot move forward until you actually wait this entire timeout, 1.5 seconds before you can do anything. Really bad. So with Shoal, the DAG advantage, it's this actually true for Bullshark as well, or any DAG-based protocol, is that novel DAG-based protocol is that validators build the DAG in network speed. You only need to wait to n-f nodes in the current round in order to move to the next round. So you can do it completely without timeouts, asynchronous, you build the DAG. So let's analyze what happened here with leaders. So we have three cases. We have a fast leader, we have a slow leader, and we have a crashed leader. So in case of a fast leader, we order it in network speed because we just A3 in this example gets enough vote and we build the DAG in the network speed, so we order it in network speed. We couldn't order it faster. Now, if you have a faulty leader, that's again perfect because I mean the leader is faulty, nothing we can do about that, right? But at least we are not paying any penalty because again the DAG advances in network speed, so there is no penalty. Immediately we continue building the next round and order the next encore. So there's no this penalty as in leader-based consensus in which you need to wait 1.5 seconds before the next leader even proposes. No, we don't have this problem. We just advance in network speed. The only question is what about slow leaders? Because in the case of slow leaders, timeouts could actually help, and sometimes they actually help because if you have a slow leader, meaning that he's not in the DAG example is not fast enough to be in the first to f plus 1 and minus f to keep gets the votes of other validators and be ordered. But if we use some timeouts to wait for the encore, then and the encore is not crashed but that's slow, maybe this little timeout would be enough, and then the encore will get enough votes and we can order it. So here is where the Shoal leader reputation come into play because what it allows us, it's not only excluded faulty validators, also included slow validators. So if you are not fast enough to be able to get enough support in like network speed, then the leader reputation will make sure your nodes are not going to be considered as encores in the future, and the protocol will move forward with like in the future only encores will only be by fast validators, and then we will be able to get like the full advantage of the network speed. So just to recap this, we call this property prevalent responsiveness, and to compare to optimistic responsiveness that was used in hot stuff. So you can see that prevalent responsiveness can achieve network speed in much more scenarios. For example, for both fast leader and slow and faulty leader, in both asynchrony and synchrony, Shoal with prevalent responsiveness achieve network speed progress, whereas hot stuff can only achieve network speed progress in the best case in which the leader is fast and we have synchrony. If we have asynchrony, whether the leader is fast or slow, we have no progress guarantee. And if we have even have synchrony with faulty leaders, hot stuff needs to pay a huge timeout penalty before making progress. Okay, as for slow leaders, with Shoal, it's in the worst case, it's 2 rounds penalty before we can order the next encore. But as I said before, if we have a good leader reputation that actually works, this scenario should be very, very rare, and slow leaders should be just excluded. Okay, so I just feel like I need to give a note about FLP, because for those of you familiar with FLP, it states that no deterministic protocol can solve consensus in asynchronous networks. And in other words, it also kind of implies that in theory, under a powerful adversary, we cannot avoid timeouts with a deterministic consensus protocol. And Bullshark, Shoal, they're all deterministic protocols. So how come we circumvent FLP? How come we have this powerful, we don't need timeouts, right? And this is a fair question. I want to talk about it. So in fact, we can't. There is a corner case in which we will not have liveness if we, in the protocol that I just described. And this case in which the adversary is like almighty, super powerful, control the network. And then what it will do is that no matter how far the DAG will progress, no encore will get enough support. There are always like not enough votes to be ordered. Like obviously it's not practical. No adversary can control the network that much, in which like no matter who is going to be the encore, we always tweak it in a way that it doesn't get enough support. But just in order to be covered from the theoretical point of view, we have the following in Shoal. So if you interpret your local DAG, and if after some amount, it's configurable, let's say X, some amount of encores that you skip and you cannot alter, then you simply fall back to using timeouts. And this will solve the problem, because then eventually with timeouts, you basically fall back to whatever liveness property we have today in Bullshark. So, but in practice, Shoal will never fall back to timeouts under all reasonable adversarial scenario, because in order for Shoal to fall back, you need to skip 10 encores in a row. Let's say if we configure X to be 10, and this is extremely, extremely unlikely, because no adversary is that powerful. Okay, just for evaluation, we compared vanilla Bullshark with Bullshark without timeout, and with Bullshark with timeouts only with one of the rounds. I didn't go into these details, but the original Bullshark has timeouts in both rounds, and we eliminate both of them. But if you're interested, you can check the paper, the Shoal paper. I won't go there. So we can see that baseline Bullshark without timeouts at all is already much better. And we are gonna, in the next evaluation, we use the Shoal Bullshark, baseline Bullshark, just in order to emphasize the contribution of the Shoal pipelining and the Shoal leader reputation. But I'm gonna skip these slides because I think I already way over time. So and just jump directly to the bottom line. So the throughput, the Shoal throughput that we show is 120K TPS. Probably could optimize it more, but the paper was about latency, and this throughput is already high enough, comparable with Bullshark and Task. The latency is sub-second, and if you compare it to vanilla Bullshark, we have 40% improvement without failures and up to 80% with failures. And if you compare to Jolteon, we have much better. Shoal has much better latency under high load. This is because obviously, if a protocol cannot handle the throughput, the transactions are queued, and then the latency is huge. And under low load, the Shoal latency and Jolteon latencies are comparable. Okay, just to summarize the talk, there is an additional material online. There is the Bullshark paper, there is the Shoal paper, and there is also the blog post that DAG meets BFT that kind of introduce all this DAG-BFT based consensus approach, if anyone wants to get more intuition about that. And here is my email, here is my Twitter handler. Happy to reach out with any questions you have. We're always happy to discuss and answer questions. Thank you so much.